Hi, welcome to the ZP Developers Zone. So today is the actual 10th of August, even though this says the 11th of August, but it's because it's in the middle of the holidays, so I've actually had to record early. That said, let's go forward. So in the ZP Developers Zone, we like to answer questions that are coming during the week. The only reason we talk fast is to try and condense everything down to being nice, quick and efficient. So today, the first question is about open source potentiostats. I've been helping somebody with open source potentiostat. This sounds a little bit strange because actually, if you know Zimmer and Peacock, you actually know that we make and sell potentiostats, and these are not your normal type of potentiostats. When I mean a normal type potentiostat, in fact, I've got one here. At least here's a sort of an early model of potentiostats, and actually potentiostats have become a lot smaller these days. Let me just be grabbing behind me. I'm just going to grab a quick potentiostat here. So here's another type of potentiostat. This will become a little bit more important actually when I talk a little bit about compliance voltage in a little bit. So potentiostats are going to appear quite a bit today, and I wasn't expecting to just go and grab those two then, but I realized they were next to me, so I thought I would. That said, let me go back to the question. The question today is about potentiostats, and I was just saying at Zimmer and Peacock, even though I'm going to talk about a open source potentiostat that somebody's building, or a homemade potentiostat, maybe I should call it that. At ZP we also produce potentiostats as well, but because the questioner is coming in from a high school, I think it's appropriate to support people, so that's what we'll do. So that said, but if you are looking for a kind of commercial potentiostat that's super slick, very up to date, this one works with my phone. I can go through between the different electrochemical methods by just scanning a QR code. And so this is also what we call cloud enabled as well. So every time I do a measurement, the data automatically goes to the cloud. Anyway, I will talk about that in a little bit more detail later on. But first of all, back to the question. So I will talk about an open source potentiostat today, though when I think about it, they're not so much made it open source, they're actually just making a homemade one. But I will support the questioner because they are coming from a high school, and I think it's appropriate to do so. Actually tied up with that a little bit is a question that's coming in about compliance voltage. A lot of people are asking about compliance voltage, and actually compliance voltage didn't used to be such a thing, let's say, that people would actually talk about. I'm just going to grab something again in fact I'll grab it here. Compliance voltage has actually become a thing. When potentiostats were large mains driven instruments like this, people weren't so talking about compliance voltage, but when they became smaller, I'll just grab it. When they became smaller and started to be kind of USB driven, then actually compliance voltage became a much more of a thing. Now when I say that, now at ZP we also have a USB powered, it's not connected to a laptop by the way, because the potentiostat that we have actually doesn't require a laptop. So this does not require a laptop, it just needs a USB power cable coming in the back there. So this is a low power device. When devices were large and bulky like this, people didn't talk about compliance voltage so much because in fact it was never a problem. But these days everything's becoming a lot more low power, and suddenly you'll find a lot more people asking questions about compliance voltage. So I am going to talk about compliance voltage this afternoon as well. I'm also going to talk about organic electrochemical transistors, whether you can use screen printed electrodes for OECTs, and the quick answer is yes, you can. I've been thinking about it for a while actually, so I'm surprised that more people are not doing that. They're kind of using well, I can understand why. If you're using the sort of semiconductor as your kind of as your material between the drain and source, then I can understand why you would be using semiconductor fabrication. But when you're doing OECTs, then actually I would actually suggest that you should actually be using screen printed electrodes. And anyway, that's my opinion, and I'll be giving you a sense of how I think that can be done. And then lastly, somebody just asked a question how to make a sodium sensor for sweat, and so I'll answer that as well. With that said, let me go forward a little bit. So upcoming webinars, if you are interested in commercializing electrochemical assays, then please don't hesitate to come to this particular webinar. It's on the 22nd of August. In fact, it's only 12 days away from now. You'll always see with our webinars we do one in the morning and one in the afternoon. that's my time zone. The reason I do that then is so that if people are in Asia, they can come to the morning one, and if they're in the Americas, they can come to the afternoon one. And Europe lucks out because the morning and afternoon do actually work for you there. So 22nd of August, we have a webinar that's really about commercialization. If you're interested in wearables, a lot of people are interested in wearables at the moment, then the 28th of August is a one particularly on wearables, so please come to that. If you're in academia or interested in translating academic research into either just for impact or actually beyond impact and onto commercialization, then please come to this webinar on the 21st of August 2024. I realize here I've written the 25th. I think I just need to correct this page, let's say, and I think I might have already actually corrected that page. With that said, I'll put any links you see popping up today. These links will also be underneath the video. Question number 1 is about open source potentiostat. So it's a chemistry school apparently. They're using DC techniques. They've been making a potentiostat. They want to do EIS, electrochemical impedance spectroscopy. They've got, I think, their own potentiostat, and then they've borrowed a couple of commercial potentiostats. One of the commercial potentiostats is kind of on this scale, so I'm kind of very familiar with these potentiostats. One of them is more or less on this scale. The scale of the potentiostat's not the point in this particular one. But what they're sort of saying is that when they have a dummy cell, they get very reproducible Nyquist plots. If you're not sure about Nyquist plots, etc., then ZP does have educational videos about this. And then they've made this homemade potentiostat, which these three potentiostats all line up when they're doing a dummy cell. And a dummy cell is just resistors, capacitors, and unsurprisingly, they, or rather credibility or credence to their capability, these potentiostats all act the same. But once they go to a screen printed electrode and a 0.5 millimolar ferrocyanide solution, they don't get the same data. And I've been advising them. As I say, I do actually have a link to open source potentiostats on the website. At ZP, I want to say now that I think the real value these days in the world of electroanalytical chemistry, sensors and biosensors is actually the development of the assays. So I hold this up, and it's developing the assays that work on electrodes like this. That's where the real value is. But I do understand that there's also a value in the value in developing your own electronics is for educational purposes. And I want to say that because potentiostats these days are almost how would you put it? They're almost commoditized. That in fact, there's so many vendors now in the potentiostat world that it's a very commoditized kind of technology. I'm part of that, of course. At ZP, we also have the sensor or potentiostat. Though I do think that this is actually the only potentiostat in the world that are commercially available that does absolutely not require a PC or a laptop, and absolutely is driven by an app that you can download off the Google Play Store or the Apple App Store, and it's absolutely cloud enabled, and it's also QR driven as well. I mean, that QR code, if I want to do EIS, which this person wants to do, let's just go to EIS, linear sweep. Yeah, there we are, EIS. It's got a really nice way of going between the different method files. No more sort of horrible menus and etc. So keep an eye out for this sensor or potentiostat, and this is the potentiostat that I will be supporting through this channel going forward. Anyway, that said, they get good consistent data between the three potentiostats when there's a dummy cell, but when they go to a ferrocyanide solution on a graphite screen printed electrode, which is not from Zimmer and Peacock, I must add, they have problems. But of course, at ZP, through this channel, we do try to support people, so I will support them, or I have been supporting them. So these are the screen printed electrodes they've been using. The biggest problem with screen printed electrodes, by the way, is if they're not from ZP, is reproducibility and sometimes stability. So I think in this case, they're suffering from stability. Though if they were to try different screen printed electrodes, they may then realize that actually, when I say different, from the same batch that they've got, and they start trying different screen printed electrodes, don't be surprised if you get quite different results. It's because actually their underlying screen printed electrodes will be quite variable. It's not a problem we suffer from at ZP. I do a whole webinar on that. If you come to the webinar for academia, you'll find out ZP solutions for that. That said, they've got these 3 potentiostats, and they've been testing the screen printed electrode on them, and they've been getting different results. So on the dummy cell, they do get this kind of nice, consistent Nyquist plot, and that's on the dummy cell. Yeah, so I was just thinking for a second, where's the diffusion characteristics? But of course, it's actually because they don't have any diffusion. It's just dummy cell. But then when they went to a graphite screen printed electrode that wasn't from Zimmer and Peacock, they do have a problem that they get quite different results from the solution when they test it on that graphite electrode. So my first inclination, or not inclination, my first thought is actually the screen printed electrode is changing every time they use it. So sometimes with screen printed electrodes, depending on what you're doing with them, in the act of making a measurement, you actually end up changing the sensor itself. So screen printed electrodes, I mean, they're really from the kind of the idea of them is from the glucose world, and in fact, you put a sample on there, you get a result, that's it. Because in using an electrode, you can actually change its state. So then when you do your first EIS and then your second and your third and your fourth, don't be super surprised if everything else stays the same, that actually you start getting drifting with screen printed electrodes. With that said, I asked them how they were doing the experiment, and I noticed that they were trying to do what I call a Faradaic EIS. By Faradaic, they've got some ferrocyanide in there, and they're applying a small. No, in fact, they're not applying. They're applying a DC offset of 0 volts, which tells me that they're not really oxidizing or reducing that ferrocyanide. You can't reduce the ferrocyanide anyway because it's already in its reduced state. But they're not oxidizing the ferrocyanide. So I actually just suggested to them that, in fact, I looked at our own data and suggested to them that I actually applied 200 millivolts. And in applying 200 millivolts, they actually came back and said, oh, it works much better now. And so when I say works much better, they're not using our ZP screen printed electrodes. If you are going to do this kind of work, then this is the ZP501. I'll put a link to it. It's a really good electrode, and it makes my life easier because I know it, it's characterized, we know everything about it. When you're trying to comment on other people's screen printed electrodes, it's hard on us because, in fact, we don't know it. And strictly speaking, sometimes maybe the vendor for that screen printed electrode should be supporting it. But at ZP, we run this channel as in part as a community, let's say for the community. Anyway, that said, I mentioned to them, look, run it with a DC offset 200 millivolts. And in fact, they now get a Nyquist plot that's much more sensible. The reason that it's smaller is because now they're actually oxidizing the ferrocyanide to ferricyanide. So they've got something called an RCT value. The charge transfer resistance is actually much smaller. So suddenly their semicircle is smaller because the charge transfer resistance is smaller. It's actually quite satisfying actually, because I realised that their solution resistance has actually stayed the same, which I would have actually hoped for, because in fact with the solution resistance they are measuring the solution resistance, and so they should have that a consistency whether they're doing it at 0 millivolts or 200 millivolts, and so they do have a good consistency. So I'm quite happy with that, and they're quite happy that they actually get better data with the 200 millivolt offset. So I think we've sort of essentially answered their question. That the problem that they had was, I think that the screen printed electrode that they're using is actually drifting with time, but in order to get, let's say, better looking, more expected data, by running that electrode at 200 millivolts, they're then working in the oxidation potential of their ferrocyanide to ferricyanide, and now they get a more classical Nyquist plot. Why? Because they're oxidizing it. The resistance has come down because, in fact, now they're at the oxidation potential, and they get this little tail which shows you that they've got a diffusion characteristic. So at least it's working in a kind of way that they would otherwise expect. But as I say, they're not using the ZP screen printed electrode, but of course at ZP we will try to support people. So that's their 0 millivolt DC offset, and then ZP suggests they went to the 200 millivolts, and that's their let's say data now. Let me go forward a little bit more. If you're interested in ZP screen printed electrodes, then please don't hesitate to check out our website. We've got a whole range of ZP screen printed electrodes. I think what makes them very different actually, is their compliance voltages. I'll talk about compliance voltage in question 2. People do really suffer from compliance voltage these days. Why? Because potentiostats are becoming smaller, they're lower power, especially the ones, there are ones now using the USB-C port on the phone. With them, you really need to use a screen printed electrode that's kind of optimized for that, and many of our screen printed electrodes are generally optimized for that. And they're also, the best thing about them is, well, A, ZP understands them, so we can support them through this channel. B, they're very reproducible, and to see that kind of data, please come to our webinars. And C, we actually, I can support them through this channel much more easily. If you're interested in ZP Tech, we do have a potentiostat of our own, and we do have, I would recommend to this particular group, start using the 501 carbon screen printed electrode, because that way I'm able to support them better. If you are planning to use a ZP screen printed electrode and you're planning to use it on your own potentiostats, make sure you get the connectors. There's nothing worse than having bad connectors when you're trying to do electrochemical experiments, because bad connectors will end up sort of really distorting the data. So I just put these connectors out there. I'm going to change to a next question now, which is really about compliance voltage. So I finished my PhD, it sounds really daft, but I finished my PhD in about 2000. And genuinely, I hardly ever touched on the subject or the term compliance voltage. Now, why was that? I was doing electrosynthesis, so electrosynthesis is a more high power, let's say, process. And I was doing electroanalytical chemistry, but my potentiostat was much more in this vein. And in fact, on the back of this, you can see there's a connector for mains electricity. So when you're running off mains electricity and you're doing, let's say, lab work, you've generally got more than enough power to actually do your electrochemistry. But once you started going to potentiostats, and I'll just change cameras for a second. Once you start going to potentiostats like this, or potentiostats like this, now I think this is really good, and actually I don't have a problem with compliance voltage because of the reasons I'm going to give you in a bit. But once you go to smaller potentiostats, you do actually start running into a compliance voltage issue. So now let's talk about compliance voltage. Right, first of all, what is compliance voltage? I'm going to say this very quickly. You can obviously rewind this a few times, but in electroanalytical chemistry, we often talk about the potential at the working electrode, which is measured versus the reference electrode. So if I say to you, if you want to oxidize ferrocyanide, then a good potential would be 200 millivolts. What I really mean by that statement is 200 millivolts versus the reference electrode, which is what I did in question number 1. Now there's another potential that's actually used, or is applied by the potentiostat, and that is between the working electrode and counter electrode, and it's called the compliance voltage. And it's to really make sure that there is sufficient current running to meet the potential being requested at that working electrode. So if I apply 500 millivolts to that working electrode in the solution of ferrocyanide, for example, it will start oxidizing. And it needs to pass current between the working electrode and counter electrode. And in order to ensure that that current is flowing, the potentiostat applies a compliance voltage. This has always been the case with potentiostats, but it wasn't a bigger. These days there's a lot more inquiries about it, and it's only come about because of the correctly so as well. The shrinkage and the low power potentiostats are now making people become much more aware of compliance potential. Sorry, I should say compliance voltage. So compliance voltage is that voltage applied between the working electrode and counter electrode to make sure there's sufficient current passing that the potential that you're asking for at the working electrode versus the reference electrode is actually maintained. Right, now if we zoom in, this counter electrode, reference electrode and working electrode, I'm going to talk about control of compliance voltage really from the perspective of screen printed electrode. So I'm going to replace that image with an image of a screen printed electrode. So I'm going to be talking about compliance voltage really from the perspective of a screen printed electrode. ZP screen printed electrodes are really, I think we actually make screen printed electrodes that often look quite different to other people's screen printed electrodes. Here's a ZP screen printed electrode. Why? Because actually we're taking an account of, I think ZP is one of the most companies most focused on helping people actually get to market. We're ISO 13485, we're contract developers, contract manufacturers for other people. And so everything we do is about getting to market, including fixing problems like compliance voltage. So most people don't even realize there is a thing called compliance voltage, because if they're using our screen printed electrodes, they're not going to suffer from it. With that said, when you look at our screen printed electrodes, and we have our working electrode, our reference electrode, which is the blue arrow, and our counter electrode, which is this black arrow. I'm using those color codes deliberately because I want to make sure that I want to enforce the kind of convention of color coding that I think that it sort of exists, but I want to kind of enforce that convention so we don't all get confused. So if you're using potentiostats, I think the red cable should go to the working electrode, the blue cable should go to the reference, and the black cable should go to the counter. And if there's a green electrode, that's for grounding your equipment. If I zoom in on this a little bit and put a solution on here, let me pretend I'm put on some ferrocyanide onto this electrode, which brings me back to question number 1, but we're on question number 2 now. So let me put some ferrocyanide on there and let me use this simulation. So I'm doing a cyclovoltammogram on my working electrodes, and what's happening here? Well, at that peak potential, I'm applying between the working and reference a potential of approximately 25 millivolts. So that's the potential at that peak, and the current that's flowing between the working and counter is about 14 microamps. Now let's just do some Ohm's law calculations on this. This is the image I got off Wiki, by the way, so I have to immediately say this came off Wikipedia. I think this image is actually a bit of a problem because it encourages people to design screen printed electrodes that look like this. And there's a few problems with this. You're going to see you're going to see me comment on the few problems in a minute. The biggest and obvious problem is actually that working electrode is so big compared to the counter electrode, and that's going to cause a compliance voltage issue in a bit. But let me come to it. So between the working and counter, I'm going to pretend there's a resistor. Now, if you are passing a current, let's say of 14 microamps, you'll often find, if you're able to see it on your instrument, that you may have a compliance voltage of about 2 volts. Not on a ZP screen printed electrode you won't, but on many screen printed electrodes you'll find it's actually 2 volts. It actually causes a problem because there's not enough compliance voltage to allow all that current to pass, and therefore you get a non-linearity in your signal versus concentration that you shouldn't otherwise had. And it's because in fact the instrument is being compliance voltage limited. So it starts to become a problem when you're using low power potentiostats, because these days, you know, they may only be getting a potential of, once upon a time it was 5 volts, these days it might be down to 3 volts. And again, I say, it wasn't a problem when you had large potentiostats, but potentiostats have got smaller. So suddenly you're expecting this signal versus concentration. You start plateauing out in the signal and you think, well, this must be my assay, but it's actually your compliance voltage. The instrument is not able to apply enough compliance voltage. You can argue that, you know, the ZP Sensei All potentiostat would also suffer that, but because of the screen printed electrodes that we manufacture that are compatible with this, we actually don't suffer from it. But with that, let me go back to the slides. So if you're trying to pass a current of 14 microamps and your compliance voltage, you're reading it at 2 volts. Just an Ohm's law calculation, this is a very kind of crude way of doing this, would mean that you would theoretically have a resistor there of 143 kiloohms. It sounds ridiculous, but strictly speaking, I should be using something called the Randall circuit, which is a more complex circuit, but I'm just treating it like a simple resistor here. So there is a way, well, first of all, a compliance voltage of 2 volts when the current passing is 40 microamps means that in fact there's a big resistor in this circuit. So the job, let's say, of the potentiostat is to be able to apply enough voltage to get through that resistor effectively. And then maybe the job of me today in this webinar is to explain to you why those resistances are so high and why and how ZP has actually overcome it. So as I say, this has become more apparent of recent, because in fact people are having these small USB-C driven potentiostats. They're nice and low power, they're very elegant, they really aid you in the sort of visualization of how you can actually form a product. But in reality, they then lead to some non-linearities in your signals versus concentration because of, in fact, they're too low power and you become in compliance voltage limited. The screen printed electrodes are often not helping in this scenario. So here's a sort of mock-up of a screen printed electrode, not one from Zimmer Peacock. But what you'll see when you dive into this then is, if I use ZP here, is the first thing that most screen printed electrodes actually get correct is distance. I want to reduce the resistance between my counter and my working electrode. So if I've got those electrodes close together or closer together, that's distance. Resistance is proportional to distance. So if I got electrodes here, that's a big resistance. If I got electrodes like this, that's a smaller resistance. So most screen printed electrodes actually do get it right, that the distance is small. So the next bit is area. If you've got a large working electrode, then you will pass a larger current. If you halve the working electrode, you often halve the current. So making a smaller working electrode is actually, from a compliance voltage perspective, quite good. But what you do find is actually people have quite large working electrodes. And then that actually then becomes another problem, which is the ratio of the working electrode and counter electrode. So I was told when I was doing my PhD that the ratio between your working electrode and counter electrode should be your counter electrode should be 10 times your working electrode. Now I think I understand now the rationale of why that statement was true, but it's not actually, strictly speaking, true. But it does help your compliance voltage to have a counter electrode that is larger than your working electrode. Now, how can I justify that? Well, the area of a resistor, the bigger you make a resistor, the less resistance it has. So if you make a very small counter electrode, it will have a higher resistance. If I increase the area of it, its resistance will go down. So in fact, area of your counter electrode is important. And if you make the working electrode smaller, you're literally going to be passing less current through it, which also helps with the compliance voltage. So areas are important. And then it brings up this third point here, which is actually ratio of working to counter. Now, as I say, when I was doing my PhD, they would say, oh, do it, 1 to 10, 1 working electrode area for 10 counter electrode areas. It doesn't have to be that gross. But in fact, when you look at this, we're not so far off it on the ZP design. So it is good to have a counter that is bigger than your working. That way it doesn't become the limiting resistance in your circuit. It should always be your working electrode that is your limiting resistor in your circuit. But the way some screen printed electrodes are designed today, it's in fact the counter electrode becomes the limiting resistor in your circuit. So distance, most people get that right. Area is okay, but actually the way we've got this one designed is quite a small area, which then cuts down the current, and the ratio of the counter electrode is much bigger, so that does actually really help. Material. So material is important. It's something that's really overlooked, in fact. So when you look at this ZP hypervalued carbon electrode, in fact my counter electrode here is actually really small, but it's made of the right material. See, in the end, I know I said resistance goes down as the area goes up. I did say that statement, but also the material. If you've got a material on your counter electrode that's easily oxidized or reduced, that also reduces your compliance voltage. So at ZP, when we're in situations where we need to make the counter electrode smaller, we overcome it by choosing the right materials. I think we're the only people that are really doing this. I can understand you can look at that and do it yourselves, but understand that ZP has been doing this for quite some time, and so often when people look at our electrodes, they think we're just being bizarre, but it's because I think we actually can see the problems because of basic experience. This is something that's important. I will get asked the question, what is your compliance potential? But actually you have a lot of control over that compliance voltage. I see using the word potential. You have a lot of control over it. So let me describe an experiment. If you do an experiment in 5 millimolar ferrocyanide, you may end up with a compliance voltage of 2 volts. If you do a cyclovoltammogram on that 5 millimolar ferrocyanide solution, but you add in 5 millimolar ferricyanide, your compliance voltage will come right down. It may even come down to close to 0. What's going on there? As you're oxidizing the ferrocyanide at your working electrode, you've given the counter electrode a nice reservoir of ferricyanide that it can reduce to ferrocyanide. It's really important. So you've given the solution, or the counter electrode rather, through the solution, something for it to do. A question that I would ask most people is, what's your counter electrode doing? And actually they don't know. What it's often doing, it could be reducing oxygen, but there's only 6 ppm, 6 parts per million of oxygen in the solution, so that can be quickly exhausted. Or it's possibly doing the hydrolysis of water, which I think is a bit of a disaster because you're starting to introduce bubbles onto your electrode system. So you can improve your compliance voltage by adding materials to your solutions that are easy for the counter electrodes to exchange electrons with. So if you ever are interested, try an experiment maybe on a screen printed electrode where your solution first of all is 5 millimolar ferrocyanide in 1 molar chloride solution, and then do the same experiment with 5 millimolar ferricyanide also present, and you'd be surprised how much the compliance voltage changes, because you've put a material in there that can easily exchange electrons with the counter electron. So you do have a control on that compliance voltage. And then just to say current, if you're doing things like if you're putting assays on electrodes, that will often, when you're putting those assays on that electrodes, when you're like putting membranes down, etc., that will end up reducing the current on the electrode, and that by reducing current on the electrode, you'll end up improving the situation with the compliance voltage. So what am I saying here very quickly? I'm saying very quickly here that things that influence the compliance voltage, especially when talking about screen printed electrodes, is distance. So the distance is something that most screen printed electrodes get right. The area is something that it's not always got right, and it does lead to high compliance voltages. The ratio of the working and counter is often not got right, and it does lead to a problem with the compliance voltage. The material is a trick that just ZP seems to be pulling at the moment, but by choosing the right material, we can get the compliance voltage right down. Solution is something that you bring to the table often. You can also tailor your solutions to help with that compliance voltage and current. I just kind of threw that one in at the end there a little bit, because if I was trying to make a glucose sensor, because I've got so many membranes involved, it often just restricts the current anyway, and by restricting the current, we end up improving the situation with the compliance voltage. So when people ask me what's your compliance voltage, it's extremely nuanced. All I can say is that we put a lot of effort into actually getting it right, and we also make a low power potentiostat, let's say, and in fact it works really well, because in fact, we also make screen printed electrodes. As long as our screen printed electrodes are being used with our potentiostat, then we've thought through all the problems that you could otherwise have with compliance voltage. Question number 3 is about organoelectrochemical transistors. The question was really, can we use screen printed electrodes to as a substrate for making OECTs on? And the quick answer is yes. I've been thinking that this should be the case for quite a while, but I'm not sure that many people are doing it. If I think about, I'll just get myself out of the way of this a little bit. If I think about these kind of organoelectrochemical transistors a little bit, they kind of involve you'll have a sort of organosemiconductive type material between the electrodes, between the drain source, and then you have a gate sort of sitting in the solution. So I'm going to describe how I would do this on a screen printed electrode. So here's my screen printed electrodes, my carbon 501. It's actually quite a good choice for this, because the cost of materials is really good, and carbon is quite inert. I think it's actually better than using something like gold, to be honest with you. What I would do is I would cast down my OECTs material. So I would cast it down between the what I call the counter and working. Don't touch the reference, because sort of then you're starting to create sort of strange shorts, let's say. So, but I would cast it down like that, at which point once it's cured, you've got your sort of material down, then you can put your drop down, and your drop will then put everything in sort of in wet contact with one another, and you should be able to use that as an organoelectrochemical transistor, an OECTs. So I hope that helps you, that yes, I think you can use screen printed electrodes as a foundation or a substrate for making OECTs. I actually think it's a really good idea, because your cost of materials and your ability to actually make materials and test materials is much, much easier. In fact, then this 501 is good, and here's some connectors that you will need. If you don't make good connection with these screen printed electrodes, then you're going to get rubbish results. But in the end, you know, the quality of an electrochemical experiment, I suppose, is always comes down to your kind of weakest component, and I don't want your connection to be your weakest component. So I hope those links will help you. Any links that pop up, by the way, I'll make sure I put them underneath the video when I finish as well. So I went a bit quick there. Question number 4 is about sodium sensors for sweat. I always have to check myself that I spelt sweat right. So the quick answer is we have definitely got videos online about making ion selective electrodes, including sodium, on this hypervalue carbon electrode. We do have a sodium sensing solution. We definitely have videos, which I will be linking to in a minute, where you can take that screen printed electrode, that sodium sensing activation solution, watch the video which I got here, and we've also got sweat patches and microfluidics, so you can actually make this sweat part as well. So the quick answer is, you were looking for guidance. I think we've got the electrodes, we've got the solution, we've got the videos, and we've got the sweat patch construction kit as well, and I hope that's good for you. Question number 1, open source potentiostat. I think I've already helped these people. I think they're actually moving on now, because, and in the end it just came down to, in that particular case, advising them to use 200 millivolts, ironically using ferrocyanide rather than the 0 millivolts that they were otherwise using. And they were using, I just occurred to me actually, they're using an AC at the moment of 50 millivolts. It's fine to use an AC of 50 millivolts, but just out of interest, it's more typical to use 5 or 10 millivolt AC, because that way then you can sort of, a lot of interpretation of impedance spectroscopy relies on this assumption of linearity, that your AC component is so small that the current response to that voltage oscillation is linear. Once you go to start going to 50 millivolts, you may actually be getting a current response that's slightly non-linear. So if you want more like classical response, you might want to reduce that AC component down to 5 millivolts. But that said, I have helped your situation a bit by telling you to use 200 millivolt DC offset. So I hope that is helping you. Don't be super surprised if you can't get good repeatability, because I'm not the supplier of your screen printed electrode, if I can put it that way. Compliance voltage. Compliance voltage is in part, has become a thing because potentiostats, this is not my potentiostat, this is another company's potentiostat. This is our potentiostat, but this one also is very small USB powered, but not requiring a laptop, etc. Because in fact, you know, rightly so, things are becoming wearable and things are becoming low power. It wasn't a problem when we had potentiostats that look like this, but potentiostats, rightly so now in electroanalytical chemistry, shouldn't look like this, because it stops people, actually, I think it stops people imagining how they will actually end up commercializing this. If you're interested in commercialization, either contact Zimmer Peacock or come to one of our webinars. But I did just show you that compliance voltage can be improved. I'm obviously biased by the use of ZP screen printed electrodes, but I did give you a sense of why we've improved compliance voltage. I also said that the compliance voltage that you otherwise need is in part governed by the solution that you put on, that you also put on there. You should be able to use the 501 screen printed electrode as a good substrate for making OECTSs on. Just make sure you use the right connector from Zimmer and Peacock. And that sodium sensor for sweat analysis, yes, ZP hypervalue carbon electrode, ZP sodium activation solution, ZP sweat patch microfluidics, and those videos should show you what to do. If you've got any questions on the DP, you can see we put quite a lot of effort into illustrating and thinking through these questions, but if you've got any questions, don't hesitate to reach out to us. Okay, take care. Thanks very much.